Okay, hello everyone. So today's topic is magnetic field due to solenoid, and we'll find out magnetic field on axis of a very long solenoid. Okay, so first we'll discuss what is the meaning of solenoid, then we'll move to ampere circuital law, and then the very important part, derivation, and there's a numerical like how to solve questions related to magnetic field due to solenoid. Okay, so a solenoid is basically a long coil of wire wrapped in many turns. So if you form a coil of wire, okay, and the radius is much smaller than the length, then it is called as solenoid. It is generally made up of copper and it is used to produce uniform magnetic field. Now remember the meaning of uniform magnetic field. So magnetic field is uniform in nature when value of magnetic field is same at all the points. So solenoid is a very good source to produce uniform magnetic field. But remember, the magnetic field will be uniform only near the axis of solenoid. So if you will move away from the axis, then value of magnetic field will change. So magnetic field will be uniform only near the axis of solenoid. Okay, now let's move to. So how will the magnetic field lines look like for a solenoid? So a solenoid is basically like a bar magnet. So on one side there is south pole and on another side there is north pole. Okay, and these are the magnetic field lines due to solenoid. So near the center of solenoid the line will be straight, and as you move away from the axis the lines will be curved. The magnetic field lines will be curved. But remember this line, that magnetic field is uniform near axis of solenoid. So basically if you connect a solenoid with a battery, then basically current will flow in the solenoid and it will generate a uniform magnetic field near axis of solenoid. So this diagram is very important, and remember the side from which the magnetic field lines enter the solenoid is south pole, and the side from which the magnetic field lines exit the solenoid is north pole. So a solenoid is equivalent to a bar magnet. Okay, now to find magnetic field, let us discuss few important things. So if there are two current carrying wires carrying the same current I, so if I take any point in between, so due to this current, the magnetic field will be inwards from right hand thumb rule, and due to this current, the magnetic field will be outwards. So between two current carrying wires, if the current is in same direction, the magnetic field inside will be zero. So between any two turns of solenoid, the magnetic field will be zero. So here also zero and here also zero. And outside the solenoid, the magnetic field is very low. So it can be taken to be equal to zero as in comparison to the magnetic field inside the solenoid. So inside the solenoid, suppose there are 1000 magnetic field lines, then at this point there will be only 2 or 3 magnetic field lines. So comparable to the inside, outside the magnetic field is zero. So if I make a loop A, B, C, D, A, then on AD also B will be equal to 0. On AB also B will be equal to 0. On DC also B will be equal to 0. So magnetic field will be only on the line from B to C. So we'll use ampere circuital law to derive magnetic field due to solenoid. So let's see how we will use the ampere circuital law. So suppose I is current in the solenoid, N is total number of turns in length L. Suppose the length of this loop is L and total number of turns inside is N. So if I'll put ampere circuital law from A to A, B dot dl equal to mu naught I enclosed. So I'll divide the integration. So from A to B, from B to C, from C to D, and from D to A equal to mu naught I enclosed. We have already discussed that from A to B, from C to D, and from D to A, B will be equal to 0. So these three terms will go to 0. And for B to C, if you'll see, we are going from B to C. Magnetic field also in same direction. So we'll write BL cos 0 is 1 equal to mu naught I enclosed. Now if you will see, in this length L there are n turns, and from every turn current I is exiting. So basically the total current will be equal to the total current enclosed inside this loop. So suppose in this figure 1, 2, 3, 4, 5, 6. So in every turn current is I, so I enclosed will be 6I. Suppose we have n number of turns, so I enclosed will be capital Ni, and B will be equal to mu naught Ni upon L, and we'll write it to be mu naught small ni, where small n is number of turns per unit length. So small n is total number of turns divided by total length, and remember to take the length to be in meter, not centimeter. Okay, so this is magnetic field due to solenoid. So near the axis of solenoid, the value of magnetic field depends on number of turns per unit length and current in the solenoid. Okay, now we'll solve one numerical related to this derivation. Suppose a solenoid of length 10 centimeter has 100 turns and carries current of 10 ampere. Find magnetic field on axis of solenoid. So B is mu naught Ni and small n will be capital N by L, that is 100 upon zero point 0.1, that is 1000, and current is 10 ampere. So magnetic field will be mu naught into 1000 into 10, that is 10 raised to power 4 mu naught Tesla. So this is magnetic field near axis of solenoid. So what you have to do is you have to write down this very important derivation in your copy. This derivation is very important. Plus also write down why we have taken magnetic field on 3 length to be equal to 0. Okay, these things are important. Okay, now you have to submit one quiz that I am sending it to you. So please submit that quiz, and if you have any doubt, you can WhatsApp me.